Hello. Let's see. Okay. You should hear me and you should see the desktop now. Does everything seem okay?
Yes, Professor.
Oh, great. Thanks. Okay. Okay. All right. So, I, 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 I thought I'd have a homework assignment up there for you. Oh, see there. I thought I'd have a homework assignment up for you today, but I don't, it's not quite ready yet. Maybe later on this evening. So there'll be an assignment 5 up there real soon. Assignment 4 was due last week. There'll be assignment 5 up. I'm still writing it. I'm almost done. So there'll be another program assignment up there soon. Okay. And then I hopefully get it up there this evening or tomorrow, and then we could talk about it on Wednesday. Okay. And today we're going to try to detail exactly what we mean by a closure. We've been kind of inching up towards this idea of a closure with these examples down here. Let me see now. Let me download the languages. Let's see, language 8 and language 7 and language 7E. 7E is kind of a funny language. It's not really a practical language. 7E was something designed just to be in between 7 and 8. Uh, 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 it's kind of meant to give you maybe some intuition about what's what's wrong with language 7 that language 8 has to solve. Okay, let me open all these. Okay. Okay, so I got these three languages. Now, let's kind of review a little bit where we were. Okay, um, let's see. Were these? I'm sorry. Oh, they're not in this folder. Okay, so let me just download them. Okay, wait, real quick. Yeah, a real simple little function. Yeah, a nested function. So the function's not at the global level; it's inside of a block. Okay. Well, okay. Now, language 7 doesn't allow this. This is what language 7E allows. Language 7E allowed this by, if you look at the grammar for the languages, language 7 only allows function definitions at the top level. Okay. So function definitions are not expressions. So inside of a begin, you can't have a function definition because inside of a begin, you can only have expressions, and expressions don't allow for defining a function. So this can't be done in language 7. It can be done in language 8. And okay, so language 8, see, fun is an expression. So begin allows expressions. And in language 8, a fun is an expression. So language 8 allows nested. Now in language 7E, the grammar is a little bit in between 7 and 8. In language 7E, fun is an expression, but not lambda. Okay. In language 8, both fun and lambda are expressions. That means we can have what are called anonymous functions. So you could have a function literal without a function name. So fun gives the function a name. See, it says here's a lambda with a name, but a lambda just is a function by itself, an anonymous function. So fun names a lambda, and lambda is really the function. Okay, so language 8 allows anonymous functions and named functions anywhere. Okay, language 7e allows named functions, but not anonymous functions. But the named functions can be anywhere. And language 7 only allows top level global functions, like in C, like the C programming language. Okay, so this example here, this is an example of a nested function. Okay, now what's wrong with nested functions? Why does language 7 and E have trouble with them? Why does language 7 avoid them? Why does C avoid them? Why does language 7E kind of have a problem? And language 8 allows them, but we have to do something special. Okay, there doesn't seem to be anything like this program will run fine in language 7E. There's nothing hard about this one, but then you can go and make things a little bit trickier. Nested first class function. What that means is the function is defined nested, but then I assign it to a global variable. And then when I call the function, I call it through its global variable. The key difference is that block is disappeared. By the time I call the function, this variable here disappears. See, this is a local variable. Okay, I create a local variable f, but then I assign the local variable to the global variable and I call the function using the global variable. But there's something a little bit flaky there. The name of the function's actually disappeared. Down here, if I say apply f to 7, I'll get undefined function f. There is no f at this point. There's a g. F itself has disappeared. So this would be an error, but this should work. Okay, and it does work. Okay, because there's nothing. We have, this is a nested function. This is a nested first class function, but there's no problem yet. Okay, then the third example has a nested function uses a non-local reference, but not a first class function. Okay, now what we have here is a nested function, and it references these variables x and y. See, the parameter is z, so x and y are those non-local. They're not part of f. They're part of this begin block. Okay, so I call f, and f gets its variables from there. Okay, that more or less makes sense. That when I call f, x and y are these local variables. Okay. Now we had to change language 7 to make this work in language 7e, because in language 7, since all functions are global, functions only get their non-local references from the global environment. Okay, so if you run this function on language 7, it'll say, I can't find x and y because it's looking for them in the global environment, not looking for them in the local environment. Okay. So this language, we had to switch language 7 to being dynamic scope for this to work, because it had to look for its local, it had to look in the local variables to find the x and y. Okay. So language 7 doesn't run this function by itself, but if we make a little change, we did this the other day, we changed language 7. That's what really made it language 7e, was we changed it to have, we changed the grammar a little bit. We changed the grammar to allow fun to be nested, and then we changed the function from lexical scope to dynamic scope. Okay, and then this will run. Okay, but then there's the next step, which was made things even more complicated. Okay. The thing that made things even more complicated was the fourth version, which needs a closure, because now we do nested, first class, and non-local reference. Okay, nested by itself, first class by itself, nested in first class, nested in non-local references, but we haven't combined all three. We still have, yeah, we haven't combined all three. Here we combine all three. Nested, first class, with non-local references. Okay, this, even dynamic scope doesn't work here. What happens is we create a local environment, put X and Y in it, define the function locally, this X and Y, which was seen to be those, assign F to the global variable G, so it escapes. We refer to this as escaping. But then at this point, all the local variables disappear. They're gone. And now when you call G, which is calling F, these variables just simply don't exist anymore. They just don't exist. The environment went away. This local environment went away, and it took the variables with it. Okay, and that's where we said that that's what a closure has to solve. Now, the only way to make this program work is you have to give it dynamic scope and declare new variables down here. Okay, if you do that, then language 7E will work here. Okay, because language 7E has dynamic scope, and this G will pick up those two variables there. When G is called here, X and Y here won't be those X and Y's, there'll be these X and Y's, which is really horrible. I mean, this is not, you know, this is language 7E with dynamic scope. Okay, these two variables just really don't matter anymore. When this function escapes, it's up to the programmer to make sure that when they call this function, they provide some kind of X and Y. Okay, now this X and Y could be moved up here and made global. Okay, in that case, this G, when it calls this F, is going to get that X and Y, not that X and Y. Okay, if you called F here, this call to F would see that X and Y, but this call to G, which is F, with the dynamic scope would see that X and Y. So this X, you don't know what it is. You know, the bottom line is that with dynamic scope, if I point to this X and say, when I call this function, what X is this? You have to answer, I have no clue. Yeah, it might be that X, it might be that X, or it might be an X down here. Okay, there might be a more recent X and Y down here. This X would just be in dynamic scope, whatever is the most recent X that was declared. It would always be the most recent X. That's what dynamic scope does. So in the dynamic running of the program, whatever was the last X declared, that's what that X is. Okay, all right. But that still doesn't solve the problem of what we originally had. Yeah, we originally had, this is what we want to solve, this. We want this to work, where this X and Y are that X and Y. That's what closures want to do. We want lexical scoping. We don't want dynamic scoping. In the history of this, back in the 70s, in the 60s and 70s, they solved this problem by just using dynamic scope. And by using dynamic scope, they could have all of this here, not a nested first class function with non-local references, but what they gave up was lexical scope. Okay. So in fact, what we want is four things: nested, first class function, non-local references, and we want lexical scope. So we want four things. And you can actually think of it. It's really important. We want one, nested functions, one, nested first class functions with non-local references and lexical scope. If you drop any one of those four, we don't need closures. If you're willing to accept dynamic scope, fine. You can have nested first-class non-local references. Okay. Otherwise, if you want lexical scope, you have to drop one of these three. You either get rid of nested functions, you get rid of first-class functions, or you get rid of non-local references. Okay. So that's the important thing to remember. If you want all four of these, you must have closures. Okay. You can get rid of any one of them and not need closures. Though if you get rid of lexical scope, you get rid of lexical scope by having dynamic scope. So getting rid of lexical scope means replacing it with dynamic scope. Get rid of nesting means you go back to language 7. Language, let's see, where is it? You get rid of nesting by changing the grammar. See, by making the definition of functions have to be at the top level, by requiring that, by not having functions being in the expression, the grammar makes the functions, this grammar makes functions not nested. Okay. So nesting comes from the grammar. Okay. First class functions, every language has first class functions. You would almost never give that up. That's it's in the grammar in the sense that when you declare a var, there's no restriction on what this guy can be here. So this guy could be, you could set, like we did here, you could set G to F. The variable G has the value of whatever the variable F is. Okay, that's just what we mean by a first class function. Once we have the name of a function, once we have a function named, we can use that name as the value of a variable. Okay, so almost nobody ever gives up first class functions. Okay, C gives up nested functions. Nobody gives up first class functions. Non-local references, some languages like Java and other languages, they give that up. They say, okay, if you have a nested function, it cannot make non-local references. Yeah. So this function f, it's okay if it's nested, but in some languages you can have nested functions, but they cannot make non-local references. Because if they make non-local references, you have to worry about escaping. You have to worry about the first class case. Okay. So you can have nested first class functions and lexical scope, but you have to get rid of the non-local references then. Okay. Yeah. So C gives up this one. Okay. Java gives up mostly this one, and it also makes it, in some places you can nest because you can have interclasses, but then you can't make non-local references. So Java plays a game of sometimes giving up this and sometimes allowing it, but where this is allowed, you don't have this. You can't make non-local references. Okay. So Java is a little bit more complicated. In modern programming, you never give up lexical scope and you never give up first-class functions. Every modern language has first-class functions and lexical scope. Dynamic scope's a mess, and without first-class functions, you can hardly program in a modern world. You can't have callback functions. You can't have GUI. It becomes almost impossible to write GUI programs. So in a sense, the first-class function and the lexical scope are given. Okay, so then it becomes a question of nested and non-local references. Okay, these are the two that have to be chosen between. C gets rid of this. Java kind of does a mixture of these. It allows a little bit of nesting with inner classes, but then they can't make non-local references. Because if you allow nested and non-local references, then you have a problem. Okay, C and C++, well, no, C++ is more like Java. It does have nested classes. So C++ is a little bit like Java. It sometimes allows you to nest things, but when you nest things, then you can no longer make non-local reference. So if you do nest a function like this, the compiler checks that this function doesn't make any references to non-local to like local variables. Okay, the nested function cannot make references to these local variables. Okay. If we want all four, we have to do something special. Okay. The language has to be designed That's where we have to be real careful about the design of the language. Okay, so that's where we need closures, and we have all four of these. Okay, the closure essentially prevents this environment from being deleted. Even though we get to this block, end of the block, which would mean that this environment goes away, we do something to make it not go away. Okay, so let's look at how we do that. It's not complicated. It's only a couple lines of code in the interpreter, but it's something that, like I mentioned several times before, it took years and years for people to sort this out and really think about what they're doing and make sense of it. And it was one guy who really figured this out in the mid 70s. So it's not a lot of code, but it did take a lot of thinking to sort this out. Okay. So in language 8, okay, if we look at the evaluator, we can see what it does to make this work. Okay. So language 8 allows nested functions. Okay. And it's going to be lexical scope. Okay. And functions, of course, are first class. So in language 8, you can have an escaping first class function that uses non-local references. Okay, so this is going to be completely allowed. Okay, but that means that somehow this environment needs to be saved. Okay, all right, so let's look at how we do that. Okay, now first we change value. Okay, here's value in language 8, and let's look at it in language 7. Okay, real minor change. The only change is this line right here. Okay, the value of a lambda is now an instruction pointer, environment pointer. The value of a lambda used to be just an instruction pointer, the tree. You pointed at the code. So L stands for lambda, I for integer, B for Boolean, L for I could have called it value F for function. I called it value L for lambda because lambda is a fancier word for function. Okay, but I could just as easily have called those value Fs. And maybe F would have been easier to understand. It's a function value. Okay, but lambda is a function value. Okay, a lambda was a tree. That was where the lambda expression was in the abstract syntax tree. Just like in C, function names point to the address in memory where the function sits. So function names in C just are memory addresses. Okay, all right, that was language 7. It's just like C. The value of function is where it is in memory. Now, the value of a function is, well, it's an IP-EP pair. So let's look up that. And we'll see that an IP-EP pair is the tree and the environment. So you read that as instruction pointer. That's the address in memory where the code is. And this thing called an environment pointer. Okay, so IP-EP pair is just two things. See, it's just a tree and an environment. Notice it's just a few lines of code. The IP-EP pair is it's by itself just 10 lines of code. Okay. It's just a way of bundling a pointer to code with a pointer to an environment. This is the environment that closes the code. If we go back to this example here, this begin block created an environment. That environment holds the variables that make this a closed expression. This is an open expression by itself because the variable z is there, but the x and y are not in here. See, you have to go up to here to get the x and y. So it takes those two lines of code to close this function. Okay, so the environment, the begin environment that holds these two variables is the thing that closes this function. Okay, go back over here. This is the tree, the code, and this is a pointer to the environment that closes the tree. So this is called a closure. I'm using the old-fashioned name here, IPEP pair, because a closure, if you look it up in any modern book, they'll tell you that a closure is two things: an address of the code and an address of the environment that closes the code, that makes the code, that gives the code all the variables it needs. So it's an instruction pointer and an environment pointer, IPEP. Okay? So this is just a, if you want, you can say this is a closure. Okay? IPEP pair is a closure. Okay, all right. So in the value object, we change value to be, instead of being only an instruction pointer, we change it to being an instruction pointer and an environment pointer. Okay, so you change value L from tree to tree and environment. So if I, yeah, so change L from tree to IPEP, which is tree and environment. Okay, right. So that's step one. You give yourself this little bit more sophisticated data structure, and then in of the value for a function, the function value now is more sophisticated. The function value is not just where the code is. The function value is where the code is and where the closing environment is. Okay. Then you have to go to the interpreter for language 8. Okay. When you create a Lambda expression, that's what, you know, when you fun doesn't really do much anymore. Fun just gives a name to a Lambda expression. So fun just names a Lambda expression. The real key is what's a Lambda expression. That's the function value. See, L for that's the thing that is the function value. So this is the thing that creates the function value. Okay. In the past, if you look in language 7 for evaluate Lambda, so let's go to language 7. Okay, handle fun did both it handled the Lambda expression. So actually in language 7, handle fun, you go to the language 7 grammar. Fun always held a Lambda expression. So the thing that handles fun handles the Lambda expression. And I only, I could have easily put this grammar up in here. I didn't really need two productions here. But since we want to prepare for language 8, so I made Lambda a separate production, even though it really isn't. It's really part of fun. So this is treated as one big production. The interpreter actually treats these two as a bundle. Okay, so the interpreter, when it handles fun, it handles a Lambda at the same time. Okay, so the language 7 interpreter goes in and, oh, let's see. See, in here, we're doing that. Okay, we're processing these two simultaneously. Okay, so first you get the variable name. That's step 1. Get the function name. Check that it's really a proper name. Check that it hasn't been defined already. So this is just some of the runtime checks. Yeah, that has to be a proper name. You can't redefine a function. Okay, then you check that you really have a Lambda over here. Okay, so you get subtree 1. See, the function name is subtree 0. So fun, subtree, left branch, right branch. Left branch is a variable, so that's these two steps. Then you get the, oh, that, well, no, I'm sorry, that's these 3 steps. get the function name, check it's a proper name, check it hasn't been already defined. And then you're ready to move over to the right-hand branch, the lambda. That's step 4. Check that it's really a lambda. Okay, check that you have the keyword lambda there. Okay, so check for this keyword there. So we see here we're treating this thing as embedded inside there. Okay, so check that you really have a lambda. Then you get the lambda expression. That's this. Well, no, I'm sorry, that's this guy. You get the lambda expression, and that's your value. Okay, so this lambda expression is the value of the function. So the variable points at that tree. Okay, that's this step 5. The value of the variable is going to be that tree, the right subbranch, lambda. Okay, so this variable points at that code. Okay, that's language 7. The variable points at the code. So that was language 7, that the value is a tree. Okay, the value is a tree. Okay, language 7. Okay, and that's what's done here. And then you're done. Oh, then you put the key value in the environment. Okay, so you take the name and you point it at the lambda in the environment. Okay, right. So that's language 7. Okay? Language 7 handles fun and lambda all at once. Now, in language 8, the fun part really doesn't matter that much. In language 8, fun is no longer really important. In fact, you can drop it from the language. You could just use var. You could just say var here. It doesn't matter if you just say var there, because variable assigns a value to a variable. Okay? So the only difference between fun is that fun specifically names a lambda, but it's no different than if you just say var variable expression, where expression is a lambda. Okay, so as I mentioned, so function declaration is redundant in language 8. Okay, you can even say, I think I had it mentioned so before. This is redundant. It's redundant with var. You don't need it. Okay, it could be eliminated from the language. Most languages keep this definition of function, like Haskell and ML. They keep it just because programmers kind of like using a separate syntax for their function definitions than their variable definitions. And it's just probably got to do with old habits. So most modern functional programming languages still have this term here, but it's redundant with this one here. Okay. All right, so what's really important is this one, which creates the function value. Okay, just like over here, we saw that it's the function value is really the important part. Okay, that's when we create over here, we get the function value. Okay, that's the lambda part. That was the lambda over here. Okay, so now look in language 8. Language 8, things get a little bit trickier. Oh, okay. Let's see. Here's evaluate fun. It pretty much does the same thing that evaluate var does. Okay. So let's see. Let me copy the grammar. Okay. So here's evaluate fun. So we're doing that piece of grammar there. Okay. So we're evaluating this piece of grammar here. So we get the variable name. That's step 1. Check that it's a proper name. Check that it hasn't been defined already. So far, that's the same as it was in language 7. Okay. check that what's over here really is a lambda. So far, all these steps are the same as they were in language 7. So far, those steps are all the same. Okay. Okay. We get the variable name. We check that it's a proper name. We check that it's not been defined already. We check that, and we check that the right-hand side really is a lambda. Var wouldn't do, this is the step that wouldn't be in a var. In a var, a variable can be declared to be anything. It could be an int, it could be a bool. So, the thing that's different about fun from var is fun only defines functions, whereas var can define any kind of variable. So this step here is the thing that distinguishes fun from var. It's not a very important difference. So fun only can declare variable names that are functions. Okay. Okay. Now this step here is different than it was over here. Okay. So if I kind of line up the code, see how there's no change? See how steps 1, 2, 3, and 4 didn't change from language 7 to language 8. Okay, there was no change. The first change is in step 5. Step 5 is the step that gets the lambda expression. Okay, this step here, which gets the function value. Okay, over here, the function value is just the lambda expression. Okay, see, the function value just is the lambda expression. Whereas over here, the function value is the closure now. So what you do is you create an IP-EP pair. Okay. This is the IP, this is the EP. Okay. Okay. Now I call evaluate lambda. Evaluate lambda is going to be I'm sorry. Evaluates this guy here. Okay. So I'm going to call evaluate lambda, whereas in language 7, all I did was just point at the lambda. Okay. Now I'm going to call evaluate lambda. Evaluate lambda says, well, that's the piece of the code that's the thing that returns the IP-EP pair. Instead of calling the constructor for IP-EP pair, it's kind of funny. You might expect that this thing would just say new IP-EP pair, but instead it calls evaluate lambda to make the code a little bit more general, and lets this guy actually instantiate the IP-EP pair, the closure for us. Okay. So we call evaluate lambda, but we give it the code and the environment. Okay. So then we go down here to evaluate lambda, and look, all it does is one line of code. See, it builds the IP-EP pair, but that makes it more general. Instead of, I could have had that line of code right there, but then that would have been less general, because this evaluate lambda is going to be called from a few other places. This won't be the only place that calls evaluate lambda. So all evaluate lambda does is it takes the tree, which is the code pointer, the environment, which is the environment pointer. That's the environment that closes off. That's the current environment. It's the environment that this function is defined in. Like in the example we did over here, that would be this begin block. See, this function is sitting inside that environment. So that would be the current environment. That current environment would hold all the variables that this function might reference. Okay. So whatever the current environment is, that's the environment that you want this function to use as its closure. Okay. So that's what we're doing here. We're saying this is the current environment. That's the environment we entered this function using. That's the current environment. So we create the closure using the current environment and the code, the code from the function and the current environment. We call evaluate lambda. All evaluate Lambda does is one line of code. It instantiates the IPEP pair, the IPEP, the closure object. Notice that there's 30 lines of comment for one line of code. That's what indicates how strange this stuff is. 30 lines of comment for, let's see, is it actually 21 lines of comments, 20 lines of comments for one line of code? Because there's so much going on here, creating a closure that closes off the code in here with the variables in here. That's the closure, that's the code, that's where that code needs to find its variables. It's non-local references, okay? And if we go back to our example, again, that was over here. This function's the code, but it's got a hole in it. What's X and what's Y? We don't want to close the X and Y off dynamically by just declaring local variables X and Y. We want X and Y to be closed by those two variables lexically. So we have to let this function point to that environment. So that function has to remember where its X and Y come from. The thing about that is that once you point to that environment, when you get to this line of code, the environment won't get deleted from memory because F pointed at that environment. G now points at an environment. G is in the global environment. So G is a reference to the environment. So the environment doesn't get garbage collected. The environment is not going to disappear on us when we get to here because G points at G holds what F held, and F holds the IPEP pair. And since the EP points to that environment, G points to that environment. So we have a live link, a live pointer to this environment, so it does not get garbage collected. If we were doing a language like, if we were writing this in C instead of Java, we'd have a problem here. Because if we go back over here to the evaluator, this environment was created when we called begin. Okay, so here's where the environment got created, by a begin block. That creates the environment. Okay, and then within that begin block, within that begin block, you evaluate the sub-expressions in the begin block. So if you look at this code over here, begin creates the local environment, and then all this code is evaluated with that local environment being the current environment. Okay. At this point here, F picks up a reference to that environment. Okay. So F picks up a reference to that environment. Then F passes that reference to G, but G is in a global environment. Okay. When we get here, we end the begin, okay, which means that we get to this part of the begin, which as it points here, that means that this local environment object becomes a garbage object. Well, actually in language 8, it doesn't necessarily become a garbage object, okay? See, that's actually, I probably should change this comment, because in language 8, in language 7, it would become a garbage object, but in language 8, it may become a garbage object. Okay, in this code here, when I get to here, the begin block ends, but because G holds a pointer to F, which holds a pointer to this block, that's not a garbage object. Okay, so may become a garbage object. Okay, so this changes here to may become a garbage object. Okay, all right. Okay, so because we have non-local reference, because we have closures now, inside this begin, when we evaluated these expressions, one of those expressions may have created a closure. Okay. Okay. And may be garbage collected, may become a garbage object, and may become a garbage collection. So then the rest of this would be one of the expressions in this begin block may have created a closure. In that case, this environment may not be a garbage object. Okay. Okay, so I should have updated the comments. That's where something really important changes from language 7 to language 8. In language 7, when you get down here to begin, evaluate begin, it's absolutely true that at this point, the object you created up here, this environment object, becomes a garbage object. Because when you return, there's no longer any reference to it. See, this local variable will be popped off the stack, but this is the local variable that pointed at that object. When this local variable disappears, this object gets garbage collected with it. Hey, that's language 7. The local variable points to the object in the heap. When you get to this return, the local variable goes away, so the object it points at gets garbage collected. In language 8, okay, in language 8, well, there's the local variable pointing at the environment object. When you get to here, the local variable definitely goes away, but one of these sub-expressions may have created a closure, which is what we have here. That created a closure. That passed the closure to a global variable. So now there's a reference to the closure, which is a reference to this environment sitting outside of this environment, sitting in the stack of the main method. There's a pointer to that environment. Okay, so this environment escapes from this code here. This environment escapes. That is no longer the only reference to that environment object. The closure we created in one of these sub-expressions can be pointing at that environment. Okay. Now, suppose we wrote this in C++. Okay. In C++, okay, we would have a reference to that object, which is okay, because that reference to that object would be in the IP-EP pair, but we'd have a problem in language if we wrote this in C++. We would not know when to garbage collect that environment. In Java, if I do the following down here, if I do here, this, suppose I change this code to do the following. Okay, so G was 0, then G became the function pointer, the closure, apply G, now set G back to 0. At that point, we lose the reference to F. We lose the reference to the closure. At that point, the closure gets garbage collected. okay, by Java. But if we wrote this in C++, we would have a hard time knowing that it's time to garbage collect the closure, okay? Because just setting a variable equal to 0 doesn't automatically trigger a garbage collection. If this was in C++, we would have to write some very tricky code that said, if G happened to be pointing at a closure and the variable G, but see, here's what could be really messy. Suppose I did this. Now, this does not trigger a garbage collection. Why not?
H has the reference.
Yeah, now H has the reference. Now, in Java, that's all done for us automatically. In Java, if I comment out this line here, then this gives rid of the reference to the closure. So the closure gets garbage collected. On the other hand, if I leave this line in here, Java keeps track of the fact that H now points at the closure. So when we set G equal to 0, there's still H pointing at the closure. If we wrote this in C++, we would have to do what's essentially called reference counting. We'd have to keep track for ourselves in our own interpreter how many, if there is a live reference to the closure or not. And when the closure no longer has a live reference, then we would have to free it from the heap, okay? See, the closure gets allocated in the heap right there. But in Java, you never free anything from the heap. That's the garbage collector's job. You never free memory in the heap in Java. That's the beauty of it. If we wrote this interpreter in C++, and it's actually one of the famous challenging, this is one of the reasons why C++ is a problem of a language. This is a classic example of something that's hard to write in C++. This program here, this interpreter becomes way harder to write in C++ than it is in Java. Not that it's a harder piece of code to write, it's just you're writing an interpreter in C++. The C++ interpreter, because it has to keep track of it has to do garbage collection on its own. It's got to do all this tricky bookkeeping of saying, oh, this creates a second reference to the IPEP, to the closure. This reduces the number of references to the closure. Then if I do this, oh, now it's time to garbage collect the closure. Okay. On the other hand, maybe not, because there may also still be a here X and H both point to the closure. Now G is zeroed out, H is zeroed out, but there's still X pointing at the closure. That's called reference counting. G points at the closure. Now X points at the closure. That's 2 references. Now H points at the closure. That's 3 references. Now G is zeroed out. So now we're down to 2 references. Now H is zeroed out. Oh, well, I'm sorry. When you get to here, F points at the closure. So that's 1 reference. Here, G points at the closure. That's 2 references. At this point, you have to count down. F is deleted, so you lose one of the references to the closure. So you're back down to 1 reference to the closure. So you have to do your own reference counting. So that's 1 reference. That's one count for the closure. That's 2 counts for the closure. Back down to 1 count for the closure. 2 counts for the closure. Back down to 1 count. No, now 3 counts for the closure. Now back down to, did I keep track of that right? We have 1 count, 2 counts, 3 counts, 2 counts, 1 count. Let's see, what's the 1 count? Oh, yeah, X, and X is the 1 count. And then if you do set X to be 0, now you garbage collect the closure. Yeah, but it can be, that code has to be written in C++. You have to explicitly do the garbage collection yourself, and it's usually done with this trick of what's called reference counting. You have to write, and notice that this one's like the tricky one. When you exit that block, you have to remember to reduce the count on the closure. That would be when you get to this return here, that return statement has to reduce the count on the closure. No, not that, on that return. That return statement has to reduce the count on the closure because this variable loses its, this variable was one of the pointers at the closure at this environment. So that reduces one of the counts to it. It's really a mess. I tried writing this code once in C++. I tried to write this interpreter in C++, and it was very hard to do. I don't even remember if I actually got it to work or not. Okay, it was way more code than the Java version because you had to do all the reference counting, and it becomes essentially, it goes from being a advanced form of Java programming to a truly advanced form of C++ programming. The kind of C++ programming that very few people know how to do. Yeah, it goes from being a Java program that most people, that you could teach in an advanced undergraduate class or a beginning graduate class. It goes from being kind of sophisticated Java programming to very sophisticated C++ programming because you're doing reference counting. Okay, and that's notoriously tricky to do and very easy to screw up. Okay. So, but you're doing the same, you're still writing, you're essentially just writing an interpreter, but you're writing an interpreter, you're switching from a garbage collected language to a non-garbage collected language. So now a huge amount of responsibility is on you as the programmer. This is why Java was invented. The Java language was invented to solve this problem. That even like this should not be something that's so hard to write in C++, but it is. Okay, and that shows you that that's now C++ gives you very fast programs, but the truth is an interpreter written in Java is just as fast as an interpreter written in C++. In the real world, a well-written interpreter written in Java is just as fast as a well-written interpreter written in C++. But the Java interpreter is much easier to write because it doesn't need to do all the garbage. It doesn't need to do it. The garbage collection is being done automatically by the Java virtual machine. The programmer doesn't have to do the garbage collection. Okay. In 99 out of 100 cases, the garbage collected Java interpreter will be just as good as the C++ reference counting interpreter. There might be a small number of places where, there might be a small number of situations where the C++ interpreter might be superior to the garbage collected Java one. But for the most part, that's not the case. Okay. For the most part, people have done a lot of testing of this, and the garbage collected Java, and that's why the Java virtual machine is real popular right now. A whole bunch of languages run on the Java virtual machine. Clojure, Scala, there's a whole Spark, a whole bunch of them run on the Java virtual machine because the garbage collection of the Java virtual machine is in 99 out of 100 times just as good as the much harder to write C++ manual garbage collection, the reference counting. The automatic garbage collection in the Java virtual machine works just as well as C++'s reference counting, but you don't have to write it. It's just built into the virtual machine for you. So, and C# is like this. The .NET runtime is just like the Java runtime. So there's a whole bunch of programming languages that run on the .NET runtime, and it's the same idea. The interpreters for those languages don't need to do reference counting. They can just depend on the .NET garbage collector. Okay, if you write an interpreter so a good example is Python. There's 3 versions of Python. There's one version that runs on a C++ written virtual machine. That's the regular version of Python. Then there's a version of Python called Jython. That's a version of Python that runs on the Java virtual machine. And many people like to use that version of Python. So it gets its garbage collection directly from the Java virtual machine. And then there's a third version of Python that runs on that .NET. See, it runs on the .NET framework. It's called Iron Python. I don't know why it was called Iron Python. Why wasn't it called .NET Python? but Iron Python runs on the .NET virtual machine, so it gets its garbage collection on. So it's a lot easier to write that interpreter for Python. You just let the job, in this case, you let the .NET virtual machine do all the garbage collection. In the case of Jython, you let the Java virtual machine do the garbage collection for you. See, when they say Java implementation, they mean that it runs on the Java virtual machine. The standard Python is actually technically called CPython. Okay, that's the standard implementation of Python. It runs, it's written in C, and it has to do its own garbage collection. And it's not faster than either of these other two, not by any means. Okay, the CPython interpreter for Python, even though it does its own garbage collection and is harder to write, it is not faster than either of these. Okay, so .NET and Java Virtual Machine, they have this, they do the garbage collection for you. It can make writing a program like what we're doing now way easier. Okay, if you wrote this interpreter in C++, you'd have to do all the garbage collection, and that would show up. That'd be exactly what's going on here. You'd have to go through all this code here and figure out at what point does the environment that we're saving in here really disappear. At what point does it really disappear? In Java, this is just nothing. This just doesn't do anything. Java would keep track of it for us. But in C++, we would have to know, oh, finally right there, you could delete the environment. And if you don't delete the environment and then you run this in a loop, see what would happen is if you run this in a loop and you didn't delete the environments when you needed to, you'd eventually run out of memory because you'd have a memory leak. So in C++, if you just ignore the environments and just never delete them, and you just never garbage collect them, that's okay for a while. But then if your program runs for more than a few hours, it very well might run out of memory because all the environments that should have been garbage collected, none of them were ever garbage collected. And so you can write this interpreter in C++, and you just don't garbage collect any of the environments. And that's okay if you run small programs or you don't run programs that run for a real long time. But if you write this in C++ and don't do the garbage collection yourself, then at some point your program can run out of memory because all these environments that should have been, every time you create an environment like a closure like this, if the closure does not get garbage collected when it should be or could be, then you could end up with uncollected garbage clogging up your heap. Your heap would fill up with objects that are no longer being used, but they've never been garbage collected. There are a lot of programs out there in the real world that work that way. That's why Windows traditionally had a need to be rebooted every day or two. There used to be a time when companies would reboot their Windows servers every day or two. And one of the reasons was because programs that did not do garbage collection very well, they'd run out of memory after a day or so. So if you rebooted them after every day, then you'd reboot them before they ran out of memory. So the rule of thumb was to reboot every day or two before they clogged up, before their heap filled up with uncollected memory, uncollected garbage. Okay, because writing C++ programs that do garbage collection is very hard. Many programs that try to do it don't do it successfully. So those are the programs that need to be rebooted every few days. So, because otherwise they'll eventually run out of memory. They have what everyone refers to as a memory leak. If you look up whoops, not there. If you Google memory leak, a program that a failure of a program to release discarded memory. When you don't delete from the heap the objects that are no longer needed. If you don't delete from the heap objects that are no longer needed. In our case, this environment's in the heap. That's the environment that holds the local variables. That's the environment that holds these local variables. At what point do you delete that environment from the heap? In language 7, delete it right away, right there. In language 7, in language 7, it got deleted right there. In language 8, it might get deleted right there if there's no closures. But if there are closures, then, this thing will get deleted from the heap whenever the Java virtual machine realizes it's no longer being used. Okay. And in that kind of code here, the Java virtual machine would figure out, oh, at this point, that closure is no longer being used. It can be reclaimed. But in a C++ program, you'd have to keep track of all that because you would have to do the release. You would have to release the memory from the heap whenever it's no longer being used. And that's really hard. Doing proper freeing of memory from heaps is the single hardest thing in C++ programming. It's the source of so many errors in C++ programming. It's one of the things that the Rust language is trying to make improvements on. Rust is a language that's trying to be as fast as C++, but not have this problem here. Okay, Java does it by having a garbage collector. Rust doesn't have a garbage collector. Rust has another clever way to try to fix this problem of memory leaks. In the Java language, you have a garbage collector. The garbage collector just figures out for itself somehow when it's time to release things from the heap. And it does the reference counting for us. The garbage collector does this reference counting for us. A C++ program has to do that reference counting itself. Okay? I don't even think people even teach this much anymore. Like if you look in the C++ courses now, almost nobody's teaching this style of programming, like how to do reference counting in C++. It's pretty tricky. And if you need to know it, you kind of have to teach it to yourself. It's not even taught much in courses. It's in the books. Like if you get a really good book on C++ programming, an advanced C++ programming book, it'll show you how to do proper memory management in C++. I mean, it's a big part of C++, but you have to read the more advanced books on how to do it. And even then, it's easy to goof up. Yeah, the books tell you how to do it, but the code is tricky, and it's very easy to mess it up. So it's notoriously difficult to get right. Okay, so that's why languages like .NET and Java said we should automate this. We should make it so that the programmer doesn't need to worry about it. The programmer allocates in the heap, and the programmer never deallocates. The programmer uses new, but the programmer never uses free anymore. In C++, you have to use new and free. In Java and .NET, you use new, but you never use free. Okay, so you get the frees for free. The frees are done for you automatically. Okay, all right. So back over here, if we go back to evaluate fun, and we compare it to the language 7, notice that there's hardly any difference. If you actually look carefully, there's a little bit of difference in that line of code and a little bit of difference in that line of code. Very, very, very small changes. Okay? A small change to that line of code and a small change to that line of code, but those small changes are profound. They make a huge difference. Okay? Language 8, language 7, tiny difference, but huge meaning. Okay? The difference here is that the value of a function is just the code itself, like in C. The value of a function is the code. In language 8, the value of a function is the code, that's the IP, the instruction pointer, and the environment that closes it off. Okay? But this is the tricky part, because once we grab onto that environment, the question then becomes, when do we release it? Okay. In the case of Java, we don't worry. Java will do that for us. Java will figure out when to release it. If we don't release it, Java will figure it out for us. And if we write this in C++, We then have the responsibility of figuring out when it's time to release that environment pointer. You know, and you, yeah, I gave you example here. It can be tricky because you could do this all day. You could create pointers to that environment, release pointer, you know, create a pointer to that environment, create a pointer to that environment, release a pointer to that environment, release a pointer to that environment. You know, you could do this as often as you want, and your code can be, you know, it has to just somehow manage to keep track of this through the whole lifetime of the program while it's running. You have to keep track of somehow this function here. Is there or is there not a reference to its environment somewhere? Do you need to keep track of the environment? How long do you keep that environment? Okay, and that's real hard to do in C++. In our case, we don't have to worry about that. Okay, all right. So from language 7 to language 8, we create this IP-EP pair. Okay, and then when we create a function value, we, instead of using just the tree, we use the IP-EP pair. That's about it. But yeah. Well, then when we call the function, then there's another change. Then when we call the function, there's a little change involved. So let's look at how it apply the function. Okay, when you call the function, you have to make a little change. Okay, here's the evaluate apply. Here's the value. Now notice that the code there, see that you can see where the change is. The change is in step 3. Okay, see, right, there's a change in step 3. Now actually, let me go down here a little bit. Line up step 4 and line up step 4 in this. Other than this, let's see. I think other than this comment, there's really not much change here. See, look. This is language 8. This is language 7. After step 4, the only difference is that there. See, trivial differences. See, so there's one variable change there, and there's one change in this line up here. So if you compare evaluate apply in language 7 with evaluate apply in language 8, there's a little change right here and a one variable change right there. Okay, there's this changes, this changes to this 3 lines of code, and this one variable here changes to this one variable here. Everything else is the same. It's amazing, tiny little changes in code. This is the part of computer science I think is really beautiful. Yeah, I don't make progress by doing gazillions of, like, writing thousands of lines of code. Make progress in computer science by writing 5 lines of code that's way more clever than the 5 lines that were before. You know, sometimes huge amounts of progress comes from just by making tiny little changes that are really clever. Okay, so all of the interpreter for language 8 differs from the interpreter language 7 in that line there, in the evaluate apply. And if you go back to evaluate fun, it was only in those 2 lines there. So if you keep track, it's about 6 lines of code. You know, the difference between these 2 interpreters is only about 6 lines of code, 6 or 8 lines of code. But this is C and this is functional programming. Yeah, this is the difference between a 1970s language and a language from the 21st century. It's a huge difference in the approach of the language. Okay, but the secret is garbage collection. If I don't have garbage collection in my language, the switch from language 7 to language 8 is not 6 lines of code. It's 106 lines of code, because the other 100 lines of code are me having to write a garbage collector in C++. Okay, and that's really one of the things that caused some that was one of the things that created, that kind of was an obstacle to making progress in this. That it wasn't just this little change, just this 8 lines of code to change here. That's the heart of the idea. But then there's the garbage collection. Who's going to free up the memory for you? Okay, that was, now, if your program doesn't run for a long period of time, you can skip the garbage collection. And there was a period of time when people did that. Some of the functional languages, they just didn't do the garbage collection. So if you ran your programs for very long, you'd run out of memory. Okay, not a big deal. If you didn't run programs for very long periods of time, you would just collect garbage in your heap. And as long as there was room in the heap, you could keep running your program. But when the heap filled up, your program might crash. Okay, so if you don't worry about garbage collection, it's just 8 or 10 lines of code from this language to this language. But if you need to run the programs for long periods of time, then you got to worry about garbage collection. In the case here, Java does it for us, or .NET would do it for us. That makes Java a beautiful language to write this in. If you have to write it in C or C++, then you have to do the garbage collection. Then language 8 is no longer a trivial step up from language 7. Language 8 is a pretty big step up, but then you have to do something. Then you're writing a garbage collector, which has not got anything to do really with this language. You're implementing garbage collection. And garbage collection is garbage collection, whether it's in a database server or a web server or an interpreter. Garbage collection is garbage collection. You're reinventing a wheel. That's one of the problems with C++. When you have to write the garbage collection, you're being forced to reinvent a wheel. You're forced to write something that should be part of your system, because every garbage collector more or less works the same, but C++ makes you re-implement the garbage collector over and over again. And it's kind of weird. Why should you re-implement garbage collector in C++ program after C++ program when all garbage collectors are more or less the same? You'd think that they would just somehow put it in the line. Now they now have things called smart pointers in C++, which do make the garbage collection a little bit easier. So C++ is better than it was 10 years ago, but it's still tricky. You're still essentially reinventing the wheel and having to write your own garbage collector for a language, for this interpreter for language 8. You essentially would have to write your own garbage collector. If you use smart pointers, it's not as hard as it used to be in the first versions of C++, but it's still tricky. But in Java, from here to here is, like we said, 8 lines of code changing. It literally just amounts to, it's no more than about 8 lines of code different. A couple lines of code in evaluate fun, and a couple lines of code in evaluate apply. Okay, all right. Okay, so that's not easy. This is not a trivial thing to be talking about. It's a lot of ideas. Even it's not a lot of lines of code, but it's a lot of ideas. Okay, so then we'll do a little bit more of this. We should look at how people make use of this in functional programming. Why do people want languages like language 8? Why do they want closures? What can they do with them? So we should look at a little bit about that kind of stuff. What is it that people think it's worth doing? Why is it worth it to do language 8 rather than, the C people thought language 7 is fine. Language 7 is essentially C. Language 8 is essentially functional programming language. C thought this was good enough. What do the functional programmers want that C doesn't have? Why do they want closures? What does it do for them? So that's what we kind of should do, is to try to get a sense of why go through this trouble of creating something that the C programmers didn't think was needed. Okay, so run out of time. Hopefully by Wednesday I'll have the next programming assignment up there, and Wednesday we can talk about the next programming assignment, and then we'll look at some of this idea, like why do people want closures in their programming languages? Okay, all right, so we'll quit there. Anybody got any last question? Any question about this stuff? Anything? It's kind of tricky. Yeah, you really should read this stuff kind of carefully. It is tricky stuff. It's not known to be easy. Any kind of question? Okay, well, okay, we'll pick up on, we'll look at more of this stuff on Wednesday. So see you on Wednesday. Bye.